In this video, we'll discuss how to conduct a z-test for a proportion, which again is used when we aren't necessarily looking particularly at a mean, but of course are looking at a percentage of a population. Now this is different than if we have a whole bunch of data that are themselves percentages. That's a slightly different case. This is if we have a whole bunch of information and are using that information to calculate a percentage. So you can revisit the confidence interval section. This correlates with that. We're going to be using the same definition of p hat as the sample proportion. But now we're going to have a hypothesized population proportion that's going to be denoted p with a little zero after it, p sub 0. We're also going to have our sample size that we'll use in the standard error calculation. Note that down below here we have p sub 0 times 1 minus p sub 0. This 1 minus p sub 0 we called q when you see the 1 minus p. We don't really have a q sub 0 per se. We do tend to just use 1 minus p sub 0 instead. Now for the assumptions, we're going to be assuming again that the sample's a random sample, and in the same way as the confidence interval before, we're going to be assuming that n times p sub 0 and n times 1 minus p sub 0 are both greater than or equal to 5, and we discussed this briefly in the confidence interval section. So for our first case, we're going to be talking about people who are trying to avoid trans fats. A news article claims that 60% of people are trying to avoid this, though our client, a dietitian, doesn't think this sounds quite right. So this client randomly selects 200 people and found that 128 of these people said that they were trying to avoid trans fats. So we're going to try to determine if this data supports the dietitian or if it supports the article. So is there enough evidence to reject the claim that the article is making about 60% or not? So we're going to conduct our hypothesis test the exact same way as always. First of all, stating the null and alternative hypothesis. For the null hypothesis, that is that the p-value, and don't get confused here, this is the proportion. This is not the p-value that we use to determine significance. So this p is proportion. Also, incidentally, my notes are wrong. This should not be p hat. It should be p. We look at the population proportions in the hypotheses. So I apologize. This should not be p hat. And because we don't have a direction, we're going to be using not equal to instead of greater than or less than. Now we're going to calculate the critical values. This uses a z critical value as in the confidence interval. So we're going to be using the z value at the alpha equals 0.05 level. Z is going to be this plus or minus 1.96 in the two-tailed test. And we can compute the test value. So using our p hat, that's the ratio that we calculated from the observed data, we found that the proportion that was observed was 64%, not 60%. We subtract this from, subtract the null hypothesis and alternative hypothesis value from this, and then divide by the standard error that's conducted under the null hypothesis. That is 0.60, the p sub 0, times 1 minus 0.6 sub 0 divided by 200. We find our test statistic to be 1.15. Now clearly 1.15 is not greater than positive 1.96. It's not smaller than negative 1.96. So this 1.15 is not going to be in the rejection region. We'll fail to reject the null hypothesis. Because of this, there's not enough evidence to reject that news article claim that the proportion of people trying to avoid trans fats is 60%. We just don't have enough evidence to reject this claim or to support the researcher's claim that it's different. Go on and give this problem a shot on your own. See how you do. Pause the screen and see how you do on this one. All right, following this up, 60% of the respondents stated it was very easy to get time off. We want to see if if it's changed recently. So in a sample of 100 people, we found 53% found it was very easy to get time off. Definitely less than 60. Our question is to see, is it enough less than 60 to be declared statistically significant, or for us to believe that it's different in the underlying population? Now we're going to test this at alpha equals 0.01. That's a little smaller than what we did last time. So the null and alternative, again, this should be written as regular p, not p hat. So p equals 0.6 and p is not equal to 0.6. That's 60%. Calculating the critical value, we find this to be plus and minus 2.58. Remember, this is a two-tailed test. Computing the test statistic, we simply plug in our numbers from the problem, that 0.53. From our observed data, the 0.60 from the null and alternative hypotheses, and we find our test statistic to be negative 1.43. Because negative 1.43 is not outside of this range of critical values, and again, if you draw the picture, you shade on the outside corners of the critical values, you'll see 1.3 is in the middle. It's in the unshaded region. This is a fail to reject. There's not enough evidence to reject this claim. There's not enough evidence to believe that the proportion is different than 60. So we don't have enough evidence to determine that the FMLA has changed over recent years. Now you can give this one a shot too. Go on and pause the screen. Give this problem a shot. All right, coming back to it. Looking to see at least 77% of the population oppose replacing bills with coins. Now, the statistician sampled 80 people and found 55% opposed at alpha equals 0.01. We want to see if this is true. That is, somebody said it was 77%. We aren't sure if we believe them or not, so we went out and collected data to test if that's true or not. So the null and alternative hypothesis, again, this should be written with p, not p hat. The null hypothesis is that it is what the other person claimed it was. The alternative is that it's not. I don't know if it's higher or lower, but I just don't think that 77% sounds right. This is the same z-values as we had earlier, plus or minus 2.58. Computing our test statistic, we find this test statistic to be negative 1.75. Though this is pretty big, it's still not outside of the critical value region, so we still fail to reject the null hypothesis. That is, that there's not enough evidence to reject the claim that is 77%. So somebody said it's 77%. I think it's a little bit lower. In fact, in my data, I found it to be 69%. But there's just not enough evidence in the data that I collected to be sure that it's not 77%. And again, if you're confused by this idea, think about if you flipped a fair coin 10 times and you flipped 6 heads. That 6 heads is not 50% heads, which you would expect in a fair coin. But that doesn't mean that it's an unfair coin. It could have just been 6 heads by chance, and it still could be a fair coin. Same thing here. It could have just been 69% by chance in my sample, and the real proportion could still be 77%. We don't have enough evidence to conclude that it's not at the alpha equals 0.01 level. So with only a 1% chance of error, we don't have enough evidence. As before, we can still incorporate p-values. It looks exactly the same process as we did with both the z-test and the t-test. So looking at this example that we just had, we state the hypothesis, same as before. Test values, same as before. We can look at the p-value. Note that the p-value is less than 0.05, but in this level, in this problem, our level of significance was 0.01. So because we are not less than the significance level of 0.01, remember, if p is less than alpha, we reject. If p is smaller than alpha, we reject. Because p is bigger than alpha, we fail to reject. And failing to reject just means that there's not enough evidence to reject the claim. All right, so we already talked at the end of Chapter 7 about tying confidence intervals and hypothesis testing together. But now that we've talked about both of them formally, let's talk about this concept more formally. So when we conduct a hypothesis test, in the hypothesis test, the level of significance relates exactly to the level of confidence of our confidence interval. In the same way, in the confidence interval, if the null hypothesis value is inside the confidence interval, let me say this one more time, if the null hypothesis value is inside the confidence interval, there's not enough evidence to reject the null hypothesis at the level of the confidence interval. So if I'm 95% confident in the confidence interval, there's not enough evidence to reject the null hypothesis at the alpha equals 0.05 level if the null hypothesis value is inside of the confidence interval. But if it's not, there is enough evidence to reject the null hypothesis at that level of significance. So let's look at this. General Electric has started advertising that their light bulbs last at least 1,100 hours long. Researchers test this claim. They install 10 light bulbs, measure how long they last, and created the following 95% confidence interval. This confidence interval, we've got 10,235 hours, roughly, to 10,896 hours, roughly. So if we want to use this confidence interval to test General Electric's claim, their null hypothesis is that it lasts 1,100 hours. Now our confidence interval doesn't contain that value 1,100. Our reasonable guess is 10,235 to 10,896. So our reasonable range is lower than that 1,100. Because 1,100 is not within the confidence interval, we reject the null hypothesis that the light bulbs last on average 1,100 hours long. And this really is what we do. We just look at the null hypothesis claim, and if it's in here, we fail to reject, and if it's not in the confidence interval, we reject. So go on and give this one a shot on your own. Pause the screen and give it a shot. Okay, coming back, we're looking to see if the nicotine content of its cigarettes is 0.644. It's measured in milligrams at the alpha equals 0.10 level. So the 90% confidence interval, now this is important. The confidence level indicates at what alpha level we tested the null hypothesis. So if I have a 90% confidence interval, I can test at alpha equals 0.10. If I have a 95% confidence interval, I can test at alpha equals 0.05. If I have a 99% confidence interval, I can test at alpha equals 0.01. So the confidence interval and alpha for the hypothesis test should match up. Now looking at this, we're trying to see if 0.644 is in this range. So 0.63, 0.65, yes, 0.64 could be within this interval, and because the null hypothesis value is within the interval, we fail to reject the null hypothesis. So this has been a video discussing z-test for proportions and then how we can use confidence intervals to test null and alternative hypothesis and to perform hypothesis testing in general. I'll say and should say that, again, the American Statistical Association highly recommends this method of testing hypothesis tests as opposed to just doing a traditional hypothesis test. Using confidence intervals is very recommended these days for how we should conduct these tests. So it's recommended that if you want to conduct a hypothesis test, you write your null hypothesis, you calculate this confidence interval according to the methods that we did in Chapter 7, and then you determine if your null hypothesis is in this range. Remember, if it is in the confidence interval, you can reject the, if it is in the confidence interval, you fail to reject the null hypothesis. If it's not in the confidence interval, you can reject the null hypothesis, determining that your data do not support that null hypothesis or that your data support an alternative. So please don't forget your journals are due after this video, so make sure you get on there and check that out. And if I'm not sure if we're going to keep going, but if we do, then the next topic that we would talk about is a two-sample hypothesis test, though after this we might have test 3 depending on where we are in your class. So if so, please make sure you're going back and reviewing the concepts we've just covered as you're preparing for test 3, and don't forget your journals.